let's talk about rational functions, specifically identifying holes in graphs. So what do I mean by a hole? Well, let's say you have a rational function. In some cases, both the numerator and the denominator of this function are going to equal 0 for some value of x. Now, as a result, the function will be undefined at this x value. So again, if there's some x value that causes the numerator to equal 0 and the denominator to equal 0, we say that the function is undefined for this value of x, and we call it a hole. It's an omitted point in the graph, meaning if we have this beautiful graph of a function and there's a hole in it, we would break for that one little piece, that would be a hole, and then we'd continue. This makes our function discontinuous at that point. So let's identify a hole in this graph, f of x, and then we're going to graph it. Okay? So let's say you're given f of x equals x squared minus 4 over x plus 2. Remember, when we want to simplify these expressions, we have to factor any place where possible. If you're not comfortable with factoring, make sure to go check out my video on factoring and simplifying expressions. So this numerator would factor into x plus 2, x minus 2, and then we've got x plus 2 in the denominator. Now, what do you notice? Well, we have x plus 2 here and x plus 2 here. So that means, you know, if you remember when we were finding undefined values of x, that meant that we were taking the denominator, setting it equal to 0, solving for x, and we'd say, okay, when x equals that value, our expression is undefined. We're just taking that a step further and we're saying, okay, it's not that it's just undefined at that expression, but if we also have that term in the numerator, it's a hole. Remember, if the numerator and the denominator of the rational function equals 0 for that particular value, we have a hole. So in this case, if x was equal to negative 2, I would have negative 2 plus 2 times x minus 2 over negative 2 plus 2. That is equal to 0. This is equal to 0. So I have 0 over 0. This is a hole. I have a hole when x equals negative 2. So that's good to know. So how do I graph this thing? Well, if you notice, because I have this like term in the numerator and the denominator, I'm allowed to cancel it out, right? So my simplified version of this function is just f of x equals x minus 2. So if I was graphing this, I know two things. I know, one, that's simplified, that the function is just equal to x minus 2, and two, I have a hole at x equals negative 2, or positive 2. X equals positive 2. I have a hole. Actually, let me double check that. No, negative 2. Okay. So my hole is at negative 2. So all that means is that, one, I'm going to graph this as if it was x minus 2. Remember that our slope would just be this coefficient, which is 1, and I'd have a y-intercept at negative 2. So that means, since b is equal to negative 2, I have a y-intercept here, and I'd follow the slope of positive 1 over 1, but I would skip over my hole where x equals negative 2. Meaning, I'd go up 1 over 1, here's a point, up 1 over 1, here's a point, and so on. But when x is equal to negative 2, which is right here, I would have a hole. So I'd have this function that looks perfect and beautiful most of the time, but has this hole when x equals negative 2. Let's practice that again. So, let's consider this function. We're going to factor it, figure out where the holes are, and then graph it. So, if I factor the numerator, I set up my x's first. I'm considering this number negative 6, and I'm asking myself, what times what equals negative 6? And using the same numbers, when I add them together, equals positive 1. How about positive 3 and negative 2? When I multiply them together, I get negative 6. When I add them together, I get positive 1. Notice that I now have an x minus 2 term in both the numerator and the denominator. That tells me two things. One, I have a whole at x equals 2, right? Because if I take x minus 2 and set it equal to 0 and solve for x, this is the value for which x is undefined, or the expression is undefined. So I have a whole at x equals 2, and my second piece of information is that simplified, if I simplify this expression, it's equivalent to x plus 3. So again, a whole at x equals 2, and if I simplify it, it equals x plus 3. So this is equivalent to x plus 3, and I have a whole at x equals 2. So if I have this function f of x equals x plus 3 and I graph it, what does that look like? I start with the y-intercept, I place it at 3. My slope is just 1 over 1, so I go up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. I can go in the other direction as well. So I have this line forming, but I have a whole at x equals 2. So I go and I look at where x equals 2, and I just write an empty circle there, signifying that I'm going to skip that spot. There is no value for the function there. Then I just fill in my line, graphing it just as normal. Okay? And there's the graph of this function. So the graphing hasn't become any harder. We still graph the same way using our y equals mx plus b as a guide, right? Where m is the slope and b is the y-intercept. We just have to also be sure to account for the whole, and we just make sure to skip over that value by representing it with an open circle. Let's do one more. Alright, so we have this function. We need to identify the whole in the graph and graph it. So what are we going to do? We're going to factor the numerator. Let me change colors here. Factor the numerator. So I set up my framework here. I consider the number -5. What times what equals -5? And using the same numbers, what plus what equals -4? Well, if I take -5 and +1 and add them together, I get -4. If I multiply them together, I get -5. So here is my factored expression. Notice that I now know that I have a whole at x equals -1. Why do I know that? Because if I take the denominator x plus 1, I set it equal to 0, and I solve for x, this is the value for which, the value of x for which the expression or the function is undefined. So I have a whole at x equals -1. Now I simplify what I've got. I've got an x plus 1 in the numerator and denominator. So simplified, I get f of x equals x minus 5. So I'm going to use these two pieces of information to graph. I know I have a whole at x equals -1, and I know that my function is equal to x minus 5. So f of x equals x minus 5, and I have a whole at x equals -1. So to graph this, I will start with my y-intercept, which is equal to -5, my slope, which is 1 over 1, so up 1 over 1, up 1 over 1, up 1 over 1, and so on and so forth, and in the other direction. So there's the outline of my line. But I have to account for that whole where x equals -1, which is right here. So I represent that with a whole, and then I would write in my solid line for the rest. So here's my graph. Notice it's a continuous line other than at the value x equals -1.